So if we're drawing this the chemical structure for these guys, what would it look like? What would the Lewis-Stock structure look like?
S in the center, or no, C carbon,
Carbon in the center.
and then oxygen and sulfur on the side.
Okay.
And 6 for those and 4 for carbon.
So we have 4 for carbon and 6 for both oxygen and sulfur.
Yeah.
Okay.
Now, does it really matter that you switch those?
No, not really.
Oh, okay. So would you have a double bond? Because
Okay. Oops. Okay, so if we're talking about the bond between carbon and oxygen, which way would polarity be going?
towards oxygen.
Okay. So is oxygen a lot stronger than carbon?
I mean, it's stronger. I don't know if it's a lot stronger.
Okay. Okay. What about, so electronegativity? Relatively speaking, is it a lot stronger than carbon?
Yes.
Okay. Now, what about sulfur and carbon?
It's going to pull towards sulfur.
So looking at, if we looked at the electronegativity, let's look at it. Let's actually do that. Hold on. I can do that. Okay, so we're looking at let's see, for electronegativity, there we go. Here's the electronegativity table. Okay. So if I look at electronegativity, so this is the maximum, that's the minimum. Okay, we have carbon right here, and we have sulfur right here.
So barely.
So barely, like minimal, right? Okay, so in that case, these areas they're almost comparable to each other. They're just a little bit, so it'd be very, very little. It'd be like a little tiny guy, right? So if we compare carbon to oxygen, a lot, right? So okay. So in that case, are we done?
With your bonds, right?
I'm done with my bonds. Yes, I'm done with my bonds. Okay, so that tells me about my bond polarity. So now tell me about my molecular polarity. We'll do that one in brown.
It's polar because it's going to be pulling towards oxygen.
Okay, so it's going to be pulling overall, the molecule is going to be pulling towards oxygen. So it's going to be doing this. So my molecular polarity is going in that direction, and it's also polar. Simple?
Dr. Henry, when would it be nonpolar?
If this was an oxygen over here,
Mm-hmm.
it would be nonpolar in that situation, because then they're pulling both in two different directions, but they're canceling each other out.
Okay.
Like what we saw in the slide last week.
Yeah. Okay.
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 Okay. So when you're canceling each other out, let's say we're looking at this guy. So if we look at the bond polarity, right, and we looked at the electronegativity, these guys are going to all have very, very small pulls towards carbon, right? So carbon is just like a little bit higher than hydrogen. And I'll show you that here in a second. Okay. And because of that, right, you're going in all directions. This guy is going to have no net no net electronegativity because these values are way too small, right? So if we take a look, let's see at our hydrogen, carbon, right? So the difference between them is 0.35, which is less than 0.04. So then it would be considered to be non-polar, right? So each of these guys, this would be like a non-polar bond. It's not really doing anything in terms of the electron moving. It's not enough energy to get over the hump. Does that make sense?
Yeah, that makes sense.
Okay, so what about this guy? Oops. This one here. What would be the center atom?
Carbon. You would attach the hydrogen on the 3 sides and then the chlorine on the other.
Okay, so we're going to put chlorine up top. Then we have hydrogens, hydrogen, hydrogen. Okay, so bond polarity between carbon and chlorine.
Chlorine.
Bond polarity between hydrogen and carbon.
Carbon.
These guys are going to be real tiny. Okay, so overall molecular polarity.
Polar.
Polar, and it's going towards
Chlorine.
okay, so it'll be polar. Simple?
Yeah.
Okay, so let's see. What if I had this? What would be would it be polar or would it be non-polar?
Wouldn't it be polar because it's still pulling towards the chlorines in 2 opposite directions now?
So it would be going in this direction between the
Yeah.
two? That's correct. So it would also still be polar. What about this guy?
Non-polar.
You said non-polar?
Because it's
Abby, why would
equal.
this be non-polar?
Wouldn't it be non-polar because like they're all pulling the same direction?
That's right. It's kind of like you being in the middle and you have quadruplets? Quadruplets, one pulling one arm this way, one pulling one arm that way, one pulling one leg this way, one pulling one leg that way. They're the exact same strength. They're totally identical in every way. So nobody has a leverage. So they're not going to be pulling you one way or the other.
Mm-hmm.
Okay.
Okay.
Does that make sense? We're
Yeah.
like like here, these are like, okay, so we have these two twins that are really hot, and then these two twins that are not so hot and really weak. So these guys are just going to be much stronger than the other guy, and you also want to go that way. So naturally, they're going to win out, right?
Yeah.
Okay. Make sense?
Yep.
Okay. Good. Okay. Oops, got carried away. Clear. Okay, so the last question of the day. Determine the dipole moment for dinitrogen sulfide and ammonia. Well, what does dinitrogen sulfide look like? Selena,
Yes.
wake up. Come on. I haven't heard anything from you this morning. You or Kayla. Don't think you guys are getting off. And I know Sadie's in there too, so. Selena, what does it
Yes,
look
Dr.
like?
Henry.
What would be the chemical formula?
It would be H2S.
Okay, so what would be the Lewis dot structure for this guy?
So would sulfur be in the center?
Okay,
And then the hydrogens would be attached next to the sulfur.
okay,
And there would be 2 sets of lone pairs on sulfur, I believe.
okay. Okay. So when we talk about the dipole moments, so we were just showing polarity in a sense, right? So we can also just show it with that arrow, right? We can also show it with those partial positive and partial negative, right? So in this context, who is going to be a little more negative than the other? Who's going to have a more electronegativity than the other?
The sulfur.
Hydrogen or sulfur, okay? So sulfur is going to have that partial negative associated with it, right? Because it's going to have the pull of the electron. We do that in a different color. And then who's going to be partial positive?
Hydrogen?
Okay, so it's the same thing as us showing those arrows. Only thing, as scientists, we like those deltas. You know, we're big on those deltas. So, but this lets us know that the electron is moving in this direction. So that means that this guy is not a complete negative, right? It's not like sodium and chloride. It's only partially. It's like a little less. It's not, they're not able to take it completely, the electron. But what happens is that they share unevenly. Sulfur gets a little bit more than hydrogen does. Okay. Now, Kayla, tell me about ammonia.
NH3.
NH3. And then who's in the center?
Nitrogen. With hydrogen on the ends, 3. And then 2 electrons on the nitrogen, lone pair.
So 1 lone pair. Okay, beautiful. So who's going to be partial positive? Who's going to be partial negative?
Partial negative, I would assume it's nitrogen.
Okay. And why do you assume that?
Because electronegativity.
Okay. So then by default, then who's going to be partial positive?
The hydrogens.
So the hydrogens. Okay, questions, concerns, Cash?
Nope.
$1 million specifically? You guys got really, really quiet. You were already quiet. I can use this to my advantage. So that means that you guys are collecting $1 million from me. That's what that means, right? There's no. So
Sure.
don't worry about it. I'll make sure that the school sends you the bill for the $1 million. Okay, so that's pretty much this chapter. How are you guys feeling about it? You feeling good?
For now.
Excellent. There's no answers.
For
Perfect.
now.
That's how we
Yeah.
feel. No comment. We
Well, that's
have
a good
no.
sign.
That's
Typically-
not a good sign.
Yeah, that is a great sign. Typically, if you have no comment, that means you understand everything so thoroughly that you don't even have any question, right?
We're processing.
We're processing. There we go.
I don't know if it still says loading across my forehead.
Oh, damn it. I did forget one thing. Okay, so there's one last thing that I wanted to say. So when
You
put,
see? Oh God.
when you put these guys in an electromagnetic field, right? What happens is that they actually orient, right? So the positive orient towards the negative, and then the negative orients to the positive. Okay? So here's the negative charge, here's the positive charge, and those molecules will actually orient that way because they're partially charged. They will adjust that. Okay. Now their mode of attraction to the positive or negative is not going to be anything. They're just going to orient themselves. So they all will be oriented the same way. So often what we'll do is we'll polarize the solution by putting a magnet on or electromagnetic field on both sides, or an electric field on both sides. So that would give that solution polarity, if we want to try to have all of the molecules facing the same way before we do something. Okay, does that make sense?
Mm-hmm.
And Cassie, you have that look. Why in the hell would you do that, right? So sometimes you may want one side of a molecule to interact with a chemical more so than the other, or interact first, because you want that to be the point of attack of a chemical reaction rather than the other end. So then you would orient it so that it's going in that direction. And then when you introduce that in the solution, then that side is going to be the one that's going to end up being attacked first. Does that make sense? So let's say we have this big old molecule. I'm just gonna say it. And we know that one side is very, very negative, okay? Phosphate.
You're drawing Woodstock?
Hey, stop making fun of my drawing here. Okay, so I have a phosphate here. So this guy, all of these guys are really negative, and then we'll make it so that these guys are real positive, or positive-ish. Let's see. Or use PE. PE.
So you play God in order to predict your
Yes, and we want
chemical outcome?
Yes, exactly. So we want the reaction to occur on this side of the compound, and we don't want it to start here. So we are playing God. So by us doing it this way, we get it all polarized, and then when we introduce let's say the reactant to it, then it's going to attack that one side first before it gets to the other side. So we'll be favored one product over another product.
Neat.
Okay, so let's stop here and then move to the next lecture. Oh, Lord Jesus Christ. Let's see.
Oh, by the way, Dr. Henry, happy Green Day.
Thank you. I got my green on. Look. See, I was prepared.
At least it's not red.
I know. That's because I haven't given out a test in a while. Let's see.
Have a beer for me.
Oh, definitely. And I'm going to put some green dye in it too. Okay. Or maybe some mint. I
Ugh.
haven't tried it.
Ugh.
Mint beer. Come on. You've never had mint beer?
Oh, I hate mint.
I love mint.
Ugh.
I have a little jungle growing in my backyard right now. And then I have spearmint, I have wild mint, and I have just standard mint. And so
I'm a
Oh,
basil
peppermint.
person. If
Peppermint.
I had basil, I'd be all over it.
well, I planted some basil and I planted some parsley, And they're growing really slow for some reason. I guess it doesn't help that one day it'll be really nice.
As
Next day it'll be
it's cold.
freezing. No. Okay, so I'm having a little trouble. Give me a second. You guys don't want to talk about accreditation. Different maybe.
So April will do a potluck and I'll just bring you the big old crock pot of corned beef for you.
That sounds delightful. Yeah,
You know how
for
many
lab.
times,
we
you know
could
how many
have-
times I've made it
Yep.
this month alone?
How many times?
Tonight will be my third time. And then
So good.
I did shepherd's pie. Well, cottage pie because I didn't have lamb. So
Ooh, shepherd's pie. I like shepherd's pie. So what is the difference between cottage pie and shepherd's pie?
lamb, shepherd's
Lamb?
pie is ground lamb, and then cottage pie is with the ground beef.
Selena, I think you'll appreciate this. Okay, Selena. So we were talking about, and I talked about it with you guys already. So when we talked about diamagnetic and paramagnetic, right? So
Yeah.
when we talk about
That's a long
diamagnetic
time
and
ago.
paramagnetic, we were talking about, at that time, we've only been talking about a single atom, right? You guys remember what diamagnetic mean and paramagnetic mean?
Yeah.
Okay, enlighten me, Kayla. Preach, girl. You're in church.
One just means, I think it's paramagnetic that makes it, like if you put up like a magnet to it, it attracts.
That's right. That's right. Para typically means P-A-R-A. It means like four. So
Or like
magnet.
non-paired electrons.
Yeah, that's right. So you have those non-paired electrons. Oh, that's a nice way of looking at it too. Non-paired electrons. Good job. And diamagnetic basically means that they're all lined up, right?
Yeah.
Okay. So here, and I had it backwards. So here we basically have liquid oxygen. Liquid oxygen between two magnets. So in this case, we have liquid oxygen between two magnets, and it actually will just sit there and stay suspended. So you look at it, that's how you get that nice little liquid feel. Although the stuff that's outside of the magnet is going to be able to flow through, but for the most part, you have that stuff that's suspended between the two, right? Where liquid nitrogen actually flows completely through, right? So we know that liquid oxygen in its natural state is what is the chemical formula?
O2.
O2. And nitrogen in its natural state is
N2.
N2. Okay. And so if we drew those structures, we know that the oxygen has how many bonds?
2.
And then, is that correct? And then we know the nitrogen has a triple bond. Okay, so although with our Lewis dot structure, we're not able to sit there and see that you have something that's unpaired, right? And if you look at it, you're like, well, it looks like everything is paired up, right? Doesn't it?
Yeah.
Okay, and then in the case of the nitrogen, you know, it also looks like everything is all paired up. So this is going to start bringing us to understanding bonds in a different manner, right? Than what we're kind of used to, right? So there's a little more complexity that goes on with that bonding situation, okay? You guys can see my screen, right?
Yep.
Yeah.
Yeah.
I know you guys will let me sit here and talk for like hours before you'll tell me. You know what it is? I really think that you guys are, your eyes are getting heavy and stuff like that. And on the back of your eyelids, you actually see those slides that I'm talking about, you know, as you're closing and trying to keep your eyes open.
You just don't want to interrupt your flow.
Okay.
Yeah.
Okay, so when we talk about bonding, so we have what we call the valence bonding theory, right? And so this is basically showing you the kind of overlap that you're going to have potentially, right? So here, this guy represents, if we look at this, what type of orbit, I mean, what type of sub shell would this guy be based upon the orbiting of the electron? Would this be an S? Would this be a P? Would this be a D? Would this be an F? Would this be a the shape?
Would it be a P?
It would be a P, right? So this would be two P's that are being shared. That would be a P from one. This will be from one atom. This will be the P from the other atom, right? And so if we look at this, this is in the X, so it would be PX because the orientation. This guy is probably our PY. Okay, so we know that when we're talking about valence bonds, or when we're talking about covalent bonds, we're sharing, we're gonna have overlapping of the two orbitals. So in this case, we have the two P's that are overlapping at the end, okay? Yeah, no, maybe?
Yeah.
Okay, so for this to kind of happen, or this theory is, it's like, so for us to form a covalent bond, to have that overlap, two conditions must be met. The orbits of the atoms must overlap, right? Because if they don't overlap, then they're not going to be able to share those electrons, right? The other thing is that you have single electrons must be combined to basically form electron pairs. So you can't have two electrons in here already on one side and two electrons in here, because we need those ones individually to overlap so that you have, in a sense, only two electrons in an orbital, right? So we can't break, whose rule was that? Was that you can't occupy an orbit with more than two electrons? You guys remember?
I want to say Huns, but I feel like
It's not Huns.
that's the
Is it the Pauli exclusion?
It is Pauli. Yes, Pauli exclusion. Yes. Okay. Huns was basically, now I'm trying to remember Huns' rule.
that was the organization one, right?
That's right. Yes.
Like okay.
And then the Offenbach principle was the how we order it up, the S, the P, the D, and then where the D starts at a slightly higher energy level than the 4S. So that's Offenbach. Okay. Let's see. So, oops, I got carried away. Okay, so now in the case of diatomic molecules, right? So the benefit of them forming a diatomic versus them being individual is energy. At the end of the day, it all deals with energy. So if you have the opportunity to get paid doing less work than what you're doing today and get paid the same amount of money or get paid even better compared to doing like 50 times more work and making the same wage that you would make otherwise, what would you do?
Work less, get more.
Work less, get more, right? Doesn't that make sense?
Yeah.
So in other words, you want to use lower amount of energy overall, right?
Yep.
Okay. Anybody disagree? Anybody just like, oh, you know what? I really like to sit there and work really hard every day, even though I don't have to, just to, I have so much free time that I just love to work for free. Anybody? Because if you do, you can come over to my house. My house needs tons and tons of cleaning, and I have tons and tons of things to do. Come on over. I have a list for you. Okay.
It's just
So
not a scroll, not just a list. It's like a scroll.
it is definitely a scroll. It goes on. Yeah. it goes on for a while. It probably reaches the Dead Sea, you know? Anyway,
Oh god.
okay, so here, this is basically showing you that concept, right? So we have this overlap. This overlap between the two hydrogens are much lower in energy compared to the hydrogens that are kind of close together. And then even when they're kind of far apart, it takes more energy to sustain this than it takes to sustain this. And so it wants to be in a state that is the lowest possible, the most stable it can possibly be. Okay, so again, it deals with energy and stability. Have you noticed there's a trend about everything? The trend? We've been talking about what again?
Energy
And
being stable.
stability, right? Chemistry is about energy and stability. The way we determine if a reaction is going to happen is based upon energy. The way we determine if a reaction is going to be stable is based upon energy, right? Okay. Okay, so here was the same figure I showed you earlier. So these are basically two p orbitals that are overlapping, right? So in this case, the A, where you have end-to-end overlap, can be better than another arrangements where we have like side catty-corner overlap. The reason why the A would be better and more stable is because you have more overlap than in this case where you have less overlap. Does
So
that
you
make
have
sense?
so you have like more surface area that are connecting.
Exactly. And so then it does a better job of rotating around the nuclei in that context compared to what you would have in this. So there are two things. So the orientation, whether it's a PY or P, because you're not going to have a PY from one and a PZ from the other kind of overlapping. You want them to be in the same type of orientation, because otherwise that way you're maximizing that overlap. Okay, does that make sense?
Yeah.
Okay, good. Okay, so shop. So I'm going to introduce you to another type of bond. Okay, so we have what we call a sigma bond. A sigma bond is basically when you have that end-to-end overlap. Okay, so here we have two S's overlapping. That's a sigma bond. Here we have an S and a P overlapping. That's also a sigma bond. Here we have two P's overlapping. This is also a sigma bond. Okay, so that single overlap is considered to be a sigma bond, not a single bond, but in most cases it is going to be a single bond. Okay, so and again, these are overlapping regions, so you're covalently interacting with each other, so the electron densities are going to be kind of mixed together in that case to allow for that overlap to occur. Okay, and then these guys, sigma bonds, are always going to be single bonds. Okay, questions, concerns, catch, credit? Okay, so now let's talk about the pi bond. Pi bond only occurs in those higher orbitals. So let me erase. Or sorry, higher subshells. So again, in this case, a pi bond will be between two p orbitals. Okay, this is from one atom, this will be from the other atom. And they're going to overlap twice. So this is like the Z, this would be PZ, so this would be PZ for our first atom, and this will be PZ for the other atom. Okay, and then you have overlapping between the two, and if that double overlap is considered to be a pi, right? Think about what a pi looks like. It has two branches. Okay, so they have to have side-to-side overlap, and these guys represent multiple bonds. So they could be, so in this case, a pi bond, you could have, let's say a double bond would be a pi bond and a sigma bond together. Okay, and a triple bond would be a sigma bond and two pi bonds. Okay, where a single bond is always just going to be a sigma bond. Does that make sense?
Kind of, yeah.
Sigmas are single. Okay.
Okay, so remember sigma, where you have a single overlap, those are always going to be single bonds. Where a double bond is going to be it could be a sigma bond and a pi bond together. A triple bond could be a sigma bond, a pi bond, or sorry, single bond and two pi bonds. Okay. Okay, let's see your skills. Okay, so we have HCl. So what type of bonds are we going to have here? And how many bonds do we have? HCl forms what type of bond?
Single.
It's a single bond. Okay, so then what type of bond would it be?
So it's sigma.
Okay, so this guy would only have a sigma bond, it would have no pi bonds. Okay, what about O2?
So would this be the sigma and pi?
Okay, so it'd be one sigma, one pi. And then what about N2?
It'd be just
be
pi,
the-
right?
It'd be the 1 sigma 2 pi.
Oh,
It'll be one sigma and two pi. That's right. Okay. Okay, so let's see those skills. So we have this nice, beautiful molecule here. So let's talk about how many total sigma bonds would this molecule have, and how many pi bonds would this molecule have?
9 sigma.
So let's count them. So there'll be 1, 2, 3, 4, 5, 6, 7, 8, 9. And then how many pies?
2.
1, 2. Piece of cake?
Yeah. But wait, there's more.
Gosh, it's like you guys know me or something. Okay. So identify the illustration as depicted as depicting a sigma or pi bond. Let's see, side-by-side overlap of 4p and 2p orbital. Okay, what is going to be the difference between a 4p orbital and a 2p orbital?
The energy?
Okay, it's going to be energy, and who's going to be bigger?
4.
Okay, 4p is going to be bigger, right? So, but they're both going to look the same. What are they going to look like? What does the p orbital look like?
Would there be 3 different orbitals in the p?
But we're talking about a single orbital in the p, right? So when we're making reference to this, we're talking about a single orbital. So, but you're right, p has 3 different orientations it could be, right? It could have 3 different orbitals, one going in the X, one going in the Y, and one going in the Z. Okay. So, but if we're going to draw a side-by-side of a 4p and a 2p orbital. Okay, so we have a 4p, one of the orbitals, side by side to a 2p orbital. How are they going to look towards each other? What is going to be the major distinction? What does the p orbital look like, first off?
I had a hard time with these. I'm trying to remember.
What does the s orbital look like?
Isn't it just the single?
What do you mean by
This-
it? Just a single what?
Single sphere, right?
Yes.
Like a
S orbital looks like a single sphere. Okay.
yeah.
So then a p orbital, so it's like a ball. So a p orbital looks like what?
An 8, or yeah, like a
It looks
Yeah.
like an 8, right?
Okay. So they're side by side, so it'd be 2 8s next to each other.
Okay, so what is going to be the difference between the 2 8s? What does that 4 and that 2 mean to us? Think about the dolls.
It's bigger. The 4 is going to be a bigger 8.
Okay, so the 4 is going to be a bigger 8. And the 2 is going to be a smaller 8. Oops. I'm trying to draw them like they're the same, so. Okay. So I'll give you their beautiful picture. Okay, does that make sense?
Yeah.
Selena, so do you understand that we're talking about a single orbital? So there's 3 orbitals in the p subshell, right?
Yeah.
So in this case, we're talking about only one of those orbitals, right? And we want them to be side to side. So is this a pi bond or is this a sigma bond?
Would it be pi because there's 2 connection or there's two bonding sites?
That's a pi. Okay. What about end-to-end overlapping of 4p orbital?
So this would be a sigma.
Okay, so this would be a sigma. And what is it going to look like?
Sideways 8s.
Okay. And the size of them, are they going to be the same size or are they going to be different sizes?
Same. Because they're both 4p.
Okay. I'll show you their pretty picture. Okay. And then the,
1 sigma.
what was that?
Why is this 1 sigma?
Because how many overlaps does it have?
Oh, okay, 1.
Yeah.
Oh, okay, never mind. Never mind.
Okay, so, and then the last one, end-to-end overlap of 4p and 2p.
So it was the same as last time, but you're gonna have one smaller, and it's a sigma.
Okay. And it's a sigma. Piece of cake?
Yep.
Okay. Okay, so now let's get to the meat.
I was hoping that was.
Okay, so the next thing that we're going to talk about is what we call hybrid. So hybrid orbitals. So hybrid atomic orbitals. So basically a hybrid atomic orbital are when you take, let's say, a P and an S, and you kind of merge them so that they're all at the same energy level. Now, this only happens when we're doing bonding. This doesn't happen in the case of the atom. Okay, does that make sense? So when we're talking about the atom, we don't have hybrid orbitals form. But when we're talking about bonding, when we get ready to bond, they form only with covalent bonds. Okay. So now when they do this, they kind of so think the s orbital is round. The p orbital are dumbbells, and the hybrid orbitals are going to be something a little bit different, right? So their shape is going to be slightly different from the atomic orbitals, and their orientation is also going to be slightly different than the atomic orbitals. Okay. So are you kind of with me right now?
Kind
Okay.
of.
So if you take a look at this guy here, this is an example. Okay, so this here is basically the overlap. So this is basically theory. So this is one P, this is another P, right? And that's what these guys are supposed to represent. And then that there is what we call would be our S orbital. Okay, so this is showing you like the hypothetical case of what happens. But in reality, this isn't quite what happens, right? And then it actually forms what we call a hybrid. Okay, and so let's see, what else should I tell you? So all of the hybrid orbitals are going to be, they're going to be equal in shape and in energy. So they're going to look exactly the same in shape and energy. And then the other thing is that, excuse me, the hybrid orbitals overlap to form only sigma bonds. So they're not going to form pi bonds. So unhybridized orbitals overlap to form pi bonds. And so all of our sigma bonds are just going to be used to form hybrid orbitals. Does that make sense? Okay. And then the last thing is that the hybrid orbitals are going to be dependent on the electron pair geometry when we talk about the Vesper theory. Okay. Okay, so now what does that mean? Come on. Okay, so here, so this kind of represents a nice little water molecule, right? So if we didn't form our nice little hybrid orbitals, then in this case, our water molecule would have that perfect 109, 109.5 separation, right? But in reality, what we do actually form is those altered, because those lone pairs orbitals, right? So this here represents a normal under non-hybrid orbital in terms of being predicted. And then this here is actually taking into consideration the two hybrid orbitals that would be forming. So in this case, we would have what we call an sp hybrid, because we need to take into consideration the bonding of two other atoms. Okay, so we'll take that S and the P and we'll kind of combine that. So one orbital from the S, one orbital from the P, and then we'll form a hybrid with both. So let me show you what that kind of looked like. Okay, let's see. Yeah. Here we go. Okay, so normally the single atom, we have, this is our 2s, that's our 2p. So for oxygen, oxygen is going to be center atom in this case, and usually the center atom is going to be forming our hybrid. So in this case, we have one electron here, one electron here, right? Is that true? I'm making stuff up. For oxygen in the S. The 2s. So doesn't it look something like that?
Yeah, because you have two and the other, yeah.
Okay.
6.
Okay. So I guess just a good example. So actually, we'll use the one that they're using, and then we'll come back to water, because then it'll be easier to see. So they're using beryllium. So in the case of beryllium, beryllium has 2 electrons in the s orbital, right? So then what beryllium is going to do is it's going to take one of these p orbitals, it's going to borrow one of these guys, and it's going to form what we call a hybrid orbital. The hybrid orbital will sit between the s and the p, so it'll be somewhere in between it. But here the p stays at the same energy level, the sp kind of goes up. So it blends both a little bit of the s and the p together to make the hybrid. And then it puts an electron in each of those. So now the sharing between chlorine and beryllium is going to be done with that sp orbital, right? So now chlorine could put that its 1 electron in here. So this will be from chlorine to sit there and make beryllium happy, right? So then you'll have, that would be chlorine making a sigma bond between it. I'm guessing it's using the s orbital. It's probably using the p orbital since should probably make it right. So this would be the p from chlorine. Okay. Does that make sense? And it's only going to form a sigma bond between these two. Okay. So if we take a look up here, so here's the S, here's the P, and then these are your SP hybrids. You kind of see how it's kind of like a deflated balloon. Like, you know, you made a balloon animal and you kind of twist in the middle, then one side is really smaller than the other, and it deflates. Are you there with me, Cassie? I think Cassie fell asleep.
No, I'm just processing the.
Take a moment, just take a
Yeah.
breather. It isn't that hard, really. Okay, so the key is here. Let me go back. Let me take a step back. Here, clear. Okay, so beryllium, we know that beryllium has 2 electrons, 2 valence electrons. Where are those valence electrons located at?
They're in the S, right?
They're in the S, okay? So when beryllium actually gets ready to bond with something, what it does, it'll borrow one of the orbitals and it'll merge these orbitals. So it takes the S and the P and it blends it together, puts it in the blender, and then you get these hybrid orbitals forming. So it's a big old circle because, you know, it's a combination of this guy and a little circle on one end. Okay, big old circle and a little circle on the other end. So that represents your hybrid. Okay, so this would be one of your SPs, and this guy would be one of your SPs. Okay, because they're half S and half P. They're like a Frankenstein monster.
So it doesn't get rid of the S shell, it just combines the two?
It combines
Okay.
the S and the P together, and then it splits it up because, you know, you had an S and a P, so you had 2 shells that are going in there, so it's going to make 2 hybrids of it. So this will be one hybrid, this will be that other hybrid. So that's what's happening right here. And then once it does that, it puts 1 electron in each so that those electrons can interact with whoever they want to interact with, in this case, chlorine.
Okay.
Okay, and if you remember, chlorine is pretty much filled. It only has 1 spot left, and that's going to be in your 3p orbital, right? So then this guy, right, if we draw it together, this basically showing you each individual one. This shows you what they look like when they're together, right, overlapping each other. So it's like you have a small bat on one side, a small bat on the other side. If you grab it on both ends, oh, where's my balloon? Here. Okay, so we have our balloon, right? So on one side of the balloon, we have the little nipple, right?
Yeah.
Okay, so that's what this guy is, kind of like our nipple. Okay, and then on the other side of the balloon, we have the same nipple, right? So, and this here represents one SP. This here represents the other SP. And so when we overlap them together and we hold it at the nipple part, then we get this guy. right? Which represents 2 new orbitals. You can't see the nipple because on each side because you have the other guy kind of blocking. Make sense?
So these actually exist, right? They're just a combination of the energies, the
Yes.
levels.
So
Okay.
so what's happening is that in one case you're upping the S energy level, but in the other case you're dropping the
Downgrading.
P energy level. So overall, if you look at it, this has a lower overall energy level than the S and the 2P up here. Okay.
Okay.
And so now these guys are able to interact with the chlorine molecule in the 3P. So this would be the 3P of the chlorine. This would be an SP. This over here would be a 3P of the other chlorine. And we'll say Cl. And this would be Be. Does that make sense?
Yeah.
Okay. Okay, so now the same thing happens in the case of when we're trying to make, so let's see, this guy is an example of the SP. This guy would be an example of the SP2, okay? So in this case, we're gonna take 1 S orbital and then 2P orbitals. So we're gonna take this guy and this guy, okay? And we're gonna take all these guys together and we're gonna blend them. And then we're gonna end up with 3 SP2 orbitals. Right. Okay, and so now, again, we have the 2 electrons here, we have the 1 electron here. So now we put these guys all so they're ready to react. So they have the ability of taking an electron next to them, right? And so this guy will allow us to sit there and interact with something else. So in the case, this would be an example is boron, right? Because boron has how many valence electrons?
3.
1, 2, 3. So it has 3 valence electrons, 1, 2, 3. And so what it does, it actually will sit there and take these 3 orbitals, 1s and 2p orbitals. That's why you get the sp2, and blend them together to form sp2. So you'd have 3 of those. So if you count the number of orbitals, there's a total of 3 orbitals. So when you get your hybrid, you should have 3 hybrid orbitals associated. Okay, and each one of them will hold an electron. Okay, so these are your 3 hybrids. This is what your 3 hybrid is going to look like. So now it looks like 3 balloons that are held together. Okay.
So do your valence electrons dictate how many hybrid levels you'll have?
For the center atom, yes.
Okay.
Yep. Okay. Or it can dictate. Okay, because it really depends on how many is actually needed.
But
Okay.
it will only dictate for the center atom always.
Yeah, because the center atom is the one that's going to be forming the hybrid. The outer atoms are just going to be using their open outer shell. That's it.
Oh, okay.
Okay. Okay, so this is basically showing you the beryllium, and then you just have, because hydrogen is only a sigma, so you're just going to have a S bond. These guys attached this way. Okay. Okay. So these are just basically examples of some sp2 hybridization. So in this case, you have oops, sorry. You have that sigma bond. So you'll have a sigma bond here, and a sigma bond here. This guy would be a pi bond. So that one is going to be a little different. So this lone pair is actually going to be held up in an sp2 orbital. Okay, where this guy, again, you're going to have an sp2 orbital, but you're going to have one pi bond. And remember, pi bonds don't form hybrids. So pi equals no hybrid. Okay. And so this guy, since there's 3 attachments, so this guy is going to have an sp2 as well. So if there's 3 attachments, you're going to have an sp3. Okay. So if there's 4 attachments, right, in terms of the electron pair geometry, then there's going to be, it's going to be an sp3 hybrid. So when we talked about water, water would be an example of an sp3 hybrid. So, oops. Okay, so for sp3 hybrid, we're basically taking into consideration all 3, the s and all 3 p orbitals together. And then you're going to be forming a total hybrid right there. In terms of your energy level, let's see. So here's an example. So in this case, we're taking all of these guys together. We're making them all the same energy. And then each one of these are called sp3 hybrids. Yeah, that look, Cassie.
Sorry.
Okay, so an example here. So this is the electron configuration for carbon, just looking at the outer shell, right? Not looking at what's in the core, right? So it's 2s, 2s2, 2 electrons in the 2s, 2p2, 1, 2, okay? So all of these guys are basically going to be mixed together, and then you're just going to get an sp3, right? All of them the same energy level. And then each of the electrons are going to be oriented the exact same way. Okay. So are you with me, or did I lose you? So in this case, okay, go ahead.
Oh, sorry. So for any element, you will use its valence electrons to create the hybrids.
That's right. Because remember, who's like, and you're talking, it's not any element, it's the element that's going to be in the center. So that center atom has to form a hybrid. And so it's more energy efficient for it to form a hybrid rather than having, you have this high p orbital, right? And then you have this s orbital. Well, this guy is in between both of those, right? So you drop overall, you're dropping the overall energy level rather than just putting the electrons here, right? And so remember, the purpose of you bonding is so that you use lower energy. Well, if you're already up here in energy, why the hell would you want to bond with anybody if you're going to still be at the same level? You want to be at a lower energy level. You want to be more stable. Does that make sense?
Okay, so it'd be the center atom, and then its valence electrons to create the hybrids
That's
in
right.
order to have the lowest possible energy.
That is correct.
Okay.
Okay. And again, we have to think of it in terms of energy. This is higher in energy. This guy. So this guy is higher in energy, than our hybrids, right? So it makes sense that, okay, so for me to be efficient, I want to sit there. And the reason why, okay, so I'm going to tell you, most people, and I'm going to be very jaded here, most people get together because of a couple of things, right? So it's either you guys are looking at it economically. Of course, there's love and stuff like that involved, but we look at things in terms of economics. So if I have 2 incomes, typically 2 incomes are better than just 1 income if we use our money appropriately, right?
Yeah.
Typically, okay? So in that context, you're saying, okay, so we both have to pay electricity. We both have to pay water. We both have to pay, you know? So if we kind of come together, you're here, I'm here, right? And then we come together, we're going to be somewhere in the middle.
So you meet in the middle,
You're meeting in the middle.
compromise.
So you guys are making a hybrid, right? Because you're no longer just Cassie. You're Cassie and what's your husband's name?
Casey.
Cassie and Casey. Oh, that's so cute. So Cassie and Casey, because you come there and you meet in the middle, right? So, and Cassie and Casey is different than just Cassie was by herself and what Casey was by. Am I right on that?
Yeah.
Right. You can't maintain that total independence when you become a couple. Okay. So it's that hybrid that's forming. So that's the same thing that's happening here. You're forming a hybrid between that p, those p orbitals and the s orbitals to try to get a more efficient orbital. Okay. Okay. So we're going to stop here. So if you guys have questions about the exam or anything like that, I have office hours tomorrow. And of course, there's the TAs. They'll help you as best they can. Sometimes I even throw questions to kind of catch them off. Okay, you guys have a good day. Bye.